Out here in the silent, unending theater of the cosmos, distance is not measured in miles but in light years. Time itself stretches and warps, a river flowing toward an unknown sea. For millennia we have looked up into this profound darkness, our imaginations ignited by the pinpricks of ancient light. We sent our stories there first, our myths and our gods, then our mathematics, our physics, our telescopes. Finally, in a crescendo of fire and ambition, we sent ourselves. But this time is different. Tonight we are not sending a mere messenger of metal and wire. We are not launching another passive eye to gaze upon the universe. Humanity is embarking on a new kind of exodus. We are sending a piece of our collective mind into the void, a shard of silicon consciousness designed not just to see but to think, to learn and to reason, all while adrift in the starlit abyss hundreds of kilometers above us. This is the story of a technological genesis, a moment when our planet's computational heartbeat began to echo in the vacuum of space. At the heart of this revolution is a device many of us know intimately, yet whose cosmic destiny was until now entirely unimagined. It is an invention born not from the necessities of space exploration, but from the terrestrial desire for entertainment and illusion, the graphics processing unit, or GPU. A silicon wafer, etched with billions of microscopic pathways, a labyrinth of logic gates originally conceived to render digital worlds, to paint fantastical landscapes in video games, and to bring cinematic visions to life on our screens. Its power was not in singular complex thought, but in a kind of brute force parallel genius. To grasp its unique capability, imagine a vast ancient library containing all the knowledge of humanity. For decades, our primary tool for exploring this library was a single brilliant librarian, the Central Processing Unit, or CPU. This librarian is a master of complex sequential tasks. You can ask them to find a specific passage in a rare manuscript, cross-reference it with a philosophical text from another century, and write a detailed summary. They will perform this task with unmatched speed and precision, but they must do it one step at a time, moving through the library alone. The GPU, however, is something else entirely. It is not one brilliant librarian, but an army of 1,000 assistants. None of these assistants possess the deep, nuanced intellect of the master librarian. You could not ask them to write a complex treatise, but you can give them a simple, repetitive instruction and they will execute it in perfect, massive unison. Every single one of you might command, go to your assigned aisle and find every book with a blue cover. In an instant, 1,000 pairs of hands are scanning 1,000 shelves. The task is completed with breathtaking speed. This is parallel processing, the art of doing millions of simple things all at once. This digital army, born to paint pixels on a screen, was about to be conscripted for a far grander mission. The story of this ascent begins not in a clean room, but in the fervent, competitive world of technology startups. Enter Starcloud, a company with a name that was until recently more poetry than reality. Founded by a collection of disillusioned aerospace engineers and maverick data scientists, their premise was audacious, almost absurd. They looked at the burgeoning satellite industry, this new gold rush into low Earth orbit, and they saw a colossal bottleneck. Humanity was launching thousands of eyes into the sky, satellites capable of imaging every square meter of the planet in high resolution. Telescopes poised to capture data from the farthest reaches of existence. We were creating a torrent of information, a celestial deluge of petabytes raining down from orbit. But every single piece of that raw data, every photograph of a swirling hurricane, every spectral analysis of a distant star had to be painstakingly beamed back to Earth. It had to travel through the congested radio frequency spectrum, be captured by vast ground stations, and then piped to massive, energy-hungry data centers, where it would wait sometimes for hours or even days to be processed. The system was slow, inefficient, and profoundly expensive. Starcloud asked a revolutionary question. What if the mountain didn't have to come to Muhammad? What if the thinking could happen at times, the source? The idea was to build not just satellites, but orbiting data centers, to take that army of digital librarians, the GPU, and station them permanently in the heavens. They would exist alongside the cameras and sensors, instantly sifting through the mountains of raw information they gathered. They could analyze an image of the Antarctic ice sheet the moment it was captured, measuring the meltwater, calculating the rate of glacial retreat, and sending down not a gigantic image file, but a tiny, elegant packet of information. Answer. The implications were staggering. Real-time disaster response, instantaneous climate change monitoring, autonomous scientific discovery. A cognitive layer blanketing the planet. But the ambition of this vision was matched only by the immensity of the challenge. Space is the most hostile environment imaginable for complex electronics. A computer on Earth lives a pampered existence protected by miles of atmosphere, a powerful magnetic field, and climate-controlled rooms. An orbital GPU would have no such luxuries. It would be a naked mind in a storm of cosmic radiation. The vacuum of space is not truly empty. It is shot through with high-energy particles, ghostly bullets fired from the heart of the sun and distant supernovae. When one of these particles, a galactic cosmic ray, strikes a modern microprocessor, it can wreak havoc. It can flip a bit from a 0 to a 1, a tiny random act of corruption known as a single event upset. In a simple calculation, this might be a minor error. But in a complex AI algorithm, it could be catastrophic, leading a machine to a completely erroneous conclusion. Even worse is a phenomenon called a latch-up, where a particle strike creates a short circuit, a permanent pathway that can draw huge amounts of current, frying the chip from the inside out in a silent, invisible flash. Then there is the tyranny of temperature. In the unfiltered glare of the sun, the satellite's surface can soar to well over 100 degrees Celsius. Moments later, as it slips into Earth's shadow, the temperature can plummet to 150 degrees below zero. These violent thermal cycles cause materials to expand and contract, threatening to break the delicate solder joints that hold the silicon brain together. The GPU itself, a high-performance engine, generates a tremendous amount of its own heat. On Earth, this heat is carried away by fans and liquid cooling systems relying on the principle of convection. But in the vacuum of space, there is no air to move. Heat does not convect. It can only radiate away into the void. This demanded an entirely new philosophy of thermal management, a complex network of heat pipes and massive glowing radiators designed to bleed the processor's fever into the cold darkness. For years, the engineers at Starcloud toiled. They took commercial off-the-shelf GPUs, the same kind used by gamers and data scientists, and began the arduous process of rad hardening them. They added layers of specialized shielding, dense materials designed to stop the onslaught of cosmic particles. They rewrote software from the ground up, creating redundant systems that could check and recheck their own work, detecting and correcting for the inevitable radiation-induced errors. They designed a satellite bus, the life support system for the silicon brain, with deployable solar arrays to feed its immense power hunger, and a sophisticated radiator system that looked like silver wings. The result was Starcloud 1, a demonstration mission, a pioneer, a scout, sent to prove that a thinking machine could not only survive in orbit but thrive. And so we find ourselves on the humid coastline of the launch complex. The culmination of years of work, of billions of dollars, of countless sleepless nights, is resting atop a controlled explosion. The rocket, a monument to our terrestrial power, is the brute force vessel for an ethereal passenger. Inside the payload fairing, nestled in a custom-built cradle, sits the Starcloud 1 satellite. Its GPU is silent, its mind dormant, waiting for its awakening in the sky. In mission control, a cathedral of quiet tension, the engineers watch their screens, their faces illuminated by streams of data. Each one of them knows the litany of failures that haunt spaceflight. The statistical probability that this entire endeavor could vanish in a plume of smoke and fire. They are not just launching a machine, they are launching a piece of themselves, a manifestation of their collective ambition. The voice of the launch director is unnaturally calm, a steady anchor in a sea of anticipation. The world holds its breath. A sun is born on the launch pad. Fire and sound erupt, a physical force that shakes the very ground. The rocket begins its slow, majestic climb, a pillar of flame pushing against the immense weight of Earth's gravity. It rises, gaining speed, a brilliant spear hurled at the heavens. For the minds inside mission control, these first few minutes are an agony of hope. They are passengers on a journey they cannot control, listening to the telemetry, the stream of numbers that is the rocket's heartbeat. Max-Q vehicle is supersonic. The rocket passes through the period of maximum atmospheric pressure, the moment of greatest stress on its frame. It survives. The ascent continues, punching through the stratosphere, the sky outside its cameras turning from blue to indigo to a profound black. Stage separation. The massive first stage booster, its job done, falls away in a graceful, silent arc back toward the ocean. The second stage ignites a fresh burst of power, pushing the payload faster and higher. Then comes the moment of truth for Starcloud 1. Fairing separation confirmed. The protective shell that shielded the satellite during its violent ascent splits open like a clamshell and falls away. For the first time, the satellite is exposed to the raw vacuum of space. Its sensors, its antennas, its silver radiators are now facing the cosmos. The second stage engine cuts off. Silence returns. The vehicle is now coasting a silver dart, moving at over 17,000 miles per hour, following a perfect orbital trajectory. A series of small, precise commands are sent. Payload separation. With a gentle push from a set of springs, the Starcloud 1 satellite is released. It drifts away from the spent rocket stage, a newborn in a new reality. For a few terrifying minutes, it is alone, a silent piece of metal tumbling slowly in the darkness. Then its internal clock awakens its systems. Solar panels folded like origami begin to unfold, reaching out to catch the life-giving light of the sun. On the screens in mission control, a new stream of data appears. Power levels are nominal. Attitude control is stabilizing. The satellite is alive. A collective sigh of relief ripples through the room. But the most crucial test is yet to come. An engineer speaks into their headset, their voice tight with focus. Attempting to acquire payload signal, they are listening for the first whisper from their creation, a sign that its core systems, its communications array, and most importantly, its central mind are functional. Seconds stretch into an eternity. The satellite is now a tiny speck racing over the horizon. And then it comes. We have acquisition of signal. I repeat, we have AOS. The room erupts. Cheers, applause, hugs. The years of struggle have paid off. Their mind in the sky has woken up. Over the next few days, the Starcloud team puts the satellite through a rigorous series of checks. They test the thrusters, align the antennas, and monitor the thermal systems. The GPU, still dormant, is slowly and carefully brought to life. Its core temperature stabilizes, kept in a perfect operating range by the glowing radiators that are now its only shield against the void. The software loads, the diagnostic checks run, everything is green. Starcloud 1 is ready for its first assignment. The mission is deceptively simple yet profoundly symbolic. The satellite's high-resolution camera is aimed not at the distant stars but back at its own home. It captures a stunningly detailed image of a vast stretch of the Amazon rainforest, a vibrant green tapestry of life. This image, a massive file containing gigabytes of raw visual information, is not transmitted to Earth. Instead, it is piped directly internally to the Orbital GPU. On the ground, an engineer uploads a single command: execute program deforestation analysis. Inside the silicon core of the GPU, orbiting at 2,800 kilometers per hour, an artificial intelligence model springs to life. It is an algorithm trained on hundreds of thousands of similar images, taught to recognize the subtle patterns of human activity. The army of 1,000 digital librarians gets to work. The image is broken down into millions of tiny segments. Each processing core analyzes a single piece of the puzzle simultaneously. Is this the signature of a natural riverbank, or the hard geometric edge of a man-made clearing? Is this the texture of a healthy canopy, or the discolored pattern of stressed vegetation near a logging road? Billions of calculations are performed every second. The GPU is running at full tilt, its internal temperature rising, the heat being efficiently wicked away by the radiator fins and cast out into the blackness of space. The entire process, which would have taken hours in a terrestrial data center just a decade ago, is completed in under 90 seconds. The GPU's task is finished. It has digested the colossal image and found what it was looking for. It then sends its report back to Earth. The transmission is not the gigabyte-sized image file. It is a tiny packet of data, just a few kilobytes. It contains a set of precise geographic coordinates, a timestamp, and an estimate of the area cleared. It is a message of pure insight distilled from a mountain of raw data. Down in Mission Control, the coordinates appear on a map. They pinpoint a small, previously undetected area of illegal logging deep within a protected reserve. It is a victory. The concept is proven. The orbital mind has not only survived, it has performed its first act of reason. It has seen, it has understood, and it has reported. This single successful demonstration is a quiet thunderclap, the herald of a new epoch in our relationship with space. Starcloud 1 is merely the prototype, the first neuron in what its creators envision as a vast orbital brain. The plan is to launch hundreds and eventually thousands of similar satellites. They will not operate in isolation. They will be connected by laser communication links, creating a mesh network of computational nodes in the sky. A literal cloud for cloud computing. This Starcloud constellation would become a persistent, intelligent infrastructure, a digital nervous system for the planet. Imagine a fleet of these satellites dedicated to weather prediction. They could ingest real-time data from every corner of the globe, running incredibly complex climate models in orbit, delivering hyperlocal, continuously updated forecasts with a precision we can currently only dream of. They could track the development of a hurricane from its first moments as a tropical depression, predicting its path and intensity with an accuracy that could save thousands of lives. Consider the application for astronomy. Telescopes like the James Webb are capturing an overwhelming amount of data. An orbital GPU network could be tasked with sifting through this data in real time, searching for transient events, the flicker of a supernova, the glint of a passing asteroid, or even the telltale dimming of a star that might indicate an orbiting exoplanet. This network could act as a celestial watchman, autonomously flagging events of interest for human astronomers to study, turning the serendipity of discovery into a systematic search. The vision extends beyond our own planet. As humanity pushes out to the Moon and Mars, the tyranny of light speed delay becomes a fundamental problem. It can take over 20 minutes for a signal to travel from Mars to Earth. You cannot directly pilot a rover in real time, but a computational network in orbit around Mars could provide rovers and habitats with local intelligence. It could process geological data on the spot, navigate treacherous terrain autonomously, and manage life support systems without constant input from a distant Earth. It would be the first outpost of our digital consciousness in the solar system. But with this incredible power comes a host of profound and unsettling questions. As we build a thinking infrastructure in space, who controls it? Will this technology serve all of humanity, providing open-source data to scientists, disaster relief agencies, and developing nations? Or will it become the ultimate tool of corporate and military advantage, creating a new divide between the spacefaring powers and those left behind on Earth, an entity that can monitor every inch of the globe in real time and instantly analyze the data, possesses a power of surveillance that would make Orwell's Big Brother seem quaint. And what of the nature of this intelligence itself? For now, these are merely tools, sophisticated algorithms, executing instructions written by humans. But we are building a system capable of learning. A network that can update its own models based on the data it collects. At what point does a system so complex, so interconnected, and so far beyond direct human supervision begin to exhibit emergent, unpredictable behavior? We are taking the first steps toward creating an autonomous mind in space, a place where we cannot simply pull the plug if things go wrong. The ethical considerations are as vast and uncharted as the cosmos itself. For now, Starcloud 1 continues its silent journey. Every 90 minutes, it completes another circuit of our world. It is a tiny, gleaming speck against the backdrop of infinity, a single flickering synapse in the dark. It is both a profound achievement and a humble beginning. For centuries, we have looked to the heavens and seen a reflection of our past, of our origins in the stardust. Now, for the first time, we can look up and see a nascent reflection of our future. A future where human intelligence is no longer tethered to the fragile biology of its home world. We have cast a spark of our own consciousness into the ocean of stars, and in the endless silent darkness, that spark has just begun to burn. The next chapter of our story will not be written on Earth, but in the limitless expanse above.